Hey folks, welcome to the Toronto Workshop. Our guest today is Tegan Maharaj, who is an assistant professor, one of my colleagues in the Faculty of Information. She has a PhD in CS from Mila, which is in Montreal, and she is an expert on AI and deep learning. And one of the things that stood out for me when Tegan was interviewing was sort of her interest in ethics and AI and like what goes actually into them and what actually how they're actually implemented in the real world. And one of those rare people who can do both the sort of, you know, hardcore CS side, but also the real world social implications. And so it is a real honor to have her along and presenting today. So thanks very much, Tegan.
My pleasure. I try anyway. I don't know, not sure how well any of that ever works, the CS stuff or the real world stuff. Let me share my screen. And you seeing my slides?
Yep.
And I can still see you. Lovely. Okay. Yeah, so today I'm going to talk to you mostly about safe and responsible AI development and sort of a little bit of I'll fly through some of my works, not trying to give you a bunch of detail about them, but just to give you some ideas of things you could ask me questions about, because I want to leave plenty of time for questions is the main idea. But I'll give you sort of my perspective on responsible AI, what I think that means, and what we need to achieve it, and then a little bit about how I'm working on that. So my first pitch to you in this direction is that AI, at our current point in history, is an important component of our everyday digital infrastructure. And therefore, we should treat AI development the way we treat building safe buildings or roads or bridges or anything like that as important public infrastructure. To give you, in case you have been living under a rock like I have with the use of Zoom controls properly, I'll just give you some examples of how pervasive AI is in our world today. So in manufacturing, AI is used to optimize facilities and to control the global supply of goods. In smart cities and planning of urban infrastructure, AI is increasingly used, smart buildings to optimize things like HVAC systems that you may have all heard more about during COVID, smart transportation like Uber and Google Maps routes are planned by AI and suggested by AI systems. Smart agriculture is increasingly used to optimize application of pesticides and herbicides and plan for anomalous events like locust outbreaks or other climate change related changes in how, environmental changes. Oh, sorry, I guess I had some of these labeled. Yeah, flight plans for aircraft even. On a more personal level, heart rate and health monitoring. Maybe some of you have apps for this quantified self kind of stuff, just now at the level I only recently learned of, like personalized gene analysis, where you can just send a letter in the mail and a couple of days later get a personalized gene analysis. And AI is often used in these tools for things like DNA matching and other biometric scanning. Increasingly used in drug discoveries. You might have heard from DeepMind, notably recently, released a huge data set of like intermediate proteins and other folding and drug chemical properties useful for drug discovery. Hospital entry triage increasingly uses AI systems to allocate people to the right person. And of course, radiography analysis of things like bone scans and other imagery uses AI heavily. And on your smartphone, I'm sure you're all aware, text correction and suggestion, voice to text and text to voice, that's called transcription, translation, anyway, translation between multiple languages. And a huge one that you may be less aware of the use of AI in is content recommendation. So from 2019, all of Google's search results now use a large language model called BERT as the basis of their search predictions, trying to figure out what you meant when you typed in your query. And also all of these other content providers, including Netflix, which now represents 80% of all content consumed online, and other services like Spotify and Amazon recommend products to you, and YouTube based on using an AI system on data from users like you and yourself, your own browsing patterns. In legal systems as well, AI is fairly pervasive. There's been a lot of press about its use to replace potentially biased human decisions in, for instance, recidivism prediction. You might have heard of the Compass system, widely used in the States, and also, but less widely publicized, in legal discovery. So this is the process where a judge or lawyers would look for prior cases that are relevant to the current case. So AI systems, much like Google search, are used for surfacing relevant casework from previous years that could be relevant. So I'm sure you can see how pervasive AI is, and how problems with AI systems, or a lack of understanding of the AI systems that we're using, could lead to potential problems. And I'll just give you one example here that you may have heard of. It was widely publicized a few years ago. There was a Twitter bot Microsoft was experimenting with, and its objective was just to make friends and become popular on Twitter. And you can see this person tweeting about it. Tay went from humans are super cool to full Nazi in less than 24 hours. This wasn't because there's any problem with, like, obviously Microsoft didn't program Tay, the bot, to be offensive in any way, but it used the data that it was given from other people about what was popular and what went viral in order to achieve its objective of becoming popular on Twitter. And unsurprisingly, controversial content is popular on Twitter. So all of that to say, there's a lot we don't understand about how AI works. And even if we understood it completely, there would be a lot of unexpected stuff that we would encounter in the practice of deploying it in the real world. So in my research, I tried to formulate experiments that would allow us to see what, or predict what would happen in future, things like unit tests and sandboxes for AI systems that would be deployed, so that we can understand behavior in advance. And all of this, I've been sort of down on AI so far, but like I'm in AI because I think it's a really cool and useful tool, and I'm really excited about applying it in a lot of important areas that I think are important, like epidemiology, climate change, and other like common good problems, physical simulation problems. I think there's a lot of really cool work that can be done with AI. And the important thing to note here that I think AI experts really need to take on a bigger level is interdisciplinary collaboration, so working with the experts in those fields so that we can avoid some mistakes that maybe have been made in rolling out AI too fast in other domains. And the third thing that I want to focus on in my research is the fact that there's no sort of overall safety or ethics standards that are typical for computer science or AI researchers to adhere to. Like I was trained in biology before my undergrad degrees in biology, and it's you learn a lot about animal testing. You go through ethics review boards, and in humanities is also common having all of these ethics and standards and third-party organizations that audit what you're doing. We need all of that in AI, I think, and I'd like to help make that happen. So these are the three areas of my research. I'll talk a little bit about them in a moment, but first I wanted to just give you some background on terms, make sure we're all on the same page. First is, I've said artificial intelligence and machine learning. Probably I've mentioned both of these terms. What do I mean by them? But when I say AI or artificial intelligence, and I think what most people mean by this is that it's just some technological system that does something that we would say requires intelligence. So it's intelligent behavior, but it's being executed by like a computer or technical system. Whereas machine learning is an algorithm or software that improves at some task with experience or data examples over time. So there are machine learning algorithms that don't do things we would consider intelligent. And there are artificial intelligence systems that don't use machine learning to achieve their intelligent behavior. Sometimes these are kind of derogatorily referred to as GoFi, good old-fashioned AI, like logic-based systems. But the kind of AI system that has achieved a lot of widespread success in the last, I don't know, 2 decades, most of the examples that I mentioned above, and what my degree is in, is something called deep learning. It's a kind of machine learning uses neural networks to learn hierarchical or deep representation. What do I mean by that? The data input is some mess of pixels that represents an image of a person or a face. The representation, this is going inside the network. What input picture can be decomposed into components like edges, faces, into contrasts at certain angles. Those contrasts at certain angles can be decomposed into pixels. So when I give a single input image to that image, but also about how all shapes break down into edges and how edges break down into pixels. So that's what allows neural network training to be more efficient, even when mathematical predictions about how many data examples it would take to learn something useful about a data distribution, mathematically, a naive approach might say that it's infeasible, but because you have this deep representation where you're learning about broken down components that are useful for other data examples, on each example, you're able to defeat what's called in machine learning the curse of dimensionality. And so, yeah, that's basically what I said, that these layered compositional features, recombining them in new ways, enables good generalization on new data examples. And I've mentioned data about, like, I don't know, 20 times so far. Underlying all of these other areas is data and information services. And so this field or this kind of question addresses things like, what does it even mean to be informative? How can we communicate things effectively to the AI systems we're designing? And how can we quantify things like bias or representation quality to address the kinds of issues I've mentioned already? So I want to go through some useful terms. Some of these I've mentioned so far, and you might already know what they are. I'll just go through them quickly. One is a data distribution. Distribution is a function that describes all of the possible values, data from different standardized ways, or it could just be what's called an empirical distribution, which is just like, I have 5 data examples, that's the distribution. The empirical distribution is just these 5 examples. But some very common ways for data to be distributed are uniform, which means equally likely across any interval, or one that you might have heard of before is Gaussian, is the bell curve. Train, validate, and test are also terms you'll hear often if you hear more about machine learning. Training is the process of adjusting the parameters to learn a model or to cause the model to learn something. And validating and test are using the model, so performing inference with that model. So typically we'll have some fixed data set and we'll separate it into 2 or 3 sets, the training set, the validation set, and the test set. So during training, usually you'll use the validation set to tune things like hyperparameters or decide on which if you're doing model selection between different models, you would use the validation set to select between those models. And then the test set is what you keep secret till the very, very end in order to have a good evaluation of what time of training machine learning models. There are other paradigms, there are other ways. For instance, in continual learning, you might not have a fixed data set that you separate this way. And in a lot of settings where you have limited data, you might do something called cross-fold validation, where you have multiple test sets that you you take a portion of the data, hold it aside, train on one part, test on the other part, and then switch which part is in the test versus training. I mentioned this term, generalization. Maybe it's an intuitive word, but to quantify what that means, it's the difference between performance on the training set and the test set. So in words, that's the ability to perform well on data that hasn't been seen during training. You'll often see a curve like this. Do you see my mouse, by the way? Thumbs up, if so, great. You'll often see a curve like this that describes this ability. So depending on the capacity of the model, if the capacity of the model is insufficient to perform well, even on the training data, you'll be in the zone called underfitting. Whereas if you have too much model capacity, at least in the traditional view, you'll get overfitting, which is sort of memorizing the training data, and the performance on the test data might degrade. And where we want to be is in this optimal capacity, and we can measure approximately where we are in underfitting versus overfitting based on the generalization error. So that different, basically the validation or the test error. Something that you might see increasingly is this term out of distribution generalization. So out of distribution means data that's not covered or not in the support of, to use the technical term, of the data distribution. So a classic example of this is in the training set, you might have pictures of cows that 90% of them are on a green background, and pictures of camels that 90% are on a yellow background. Well, an out of distribution task or an out of distribution test set would be if none of the cows appear on a green background and none of the camels appear on a yellow background. And this kind of problem is, of course, interesting for real world AI because it's not typically the case that a test set is a perfect sort of measure of what we actually want an algorithm to have learned. And that brings me to a problem called specification, which is also something that you may have heard of recently. There's a big paper out of Google a year or two ago about this. Specification is the formalization of some real world problem we want to address into a technical setting. So for instance, training, testing, which algorithms we use for the training procedure, how large the data set is, all of these factors form part of the specification. And there's always a specification gap, a difference between the real problem that we want to address versus the thing that we are able to operationalize or communicate to an AI system. And this leads to a problem that there's a really cool book about that I'll mention later called alignment, which is getting AI systems to understand or act in accordance with what we actually really want. That's the alignment problem. And as you may have encountered yourself, trying to type something into your phone and the autocorrect doesn't understand what you're actually trying to get across. This has a lack of alignment between real world systems and what we actually want is a problem from the small level to the very big level with when you have AI systems deployed in the real world. All right, so I've mentioned responsible AI development. What do we, in order to know what we want for this, first let's start with what do we have, and this is a picture, sort of a cartoon of AI development that I really like. I would say that this picture sort of describes what we currently have for the process of AI development. There's sort of a lack of understanding of the system's principles, because the solution is piecemeal and poorly tested and maybe unanticipated. So most AI systems are built by something I'm saying is analogous to this, like forklift on a forklift on a forklift with I don't know, maybe this guy is trying to do some safety by he's standing on the forklift and holding the other forklift there. I'm not really sure, but overall, there's a lack of guidelines, there's self-regulation, and probably none of even if these components were tested to be very safe and ethical and responsible and everything, they're going to be put together in novel ways in the real world that are not anticipated in advance. And we need to deal with that somehow. So how can we start to deal with these problems. I mentioned the three ways before, but I'll go through them in a bit more detail. One is foundational science, so statistical learning theory, empirical understanding, stuff like generalization, sample complexity proofs, data-dependent bounds on generalization, and just experiments that elucidate how deep networks or other AI systems will perform in a setting that is closer to what they will encounter in the real world. To address both of these two, we also need, as I mentioned before, multidisciplinary collaboration so that we, as AI developers, know what the real world situation is like that an AI system would be deployed in, and so that we can make more accurate models of it and make better use of experts' time and ability to, for instance, re-annotate data or give us feedback on what is or isn't working in the AI system. So this would include things like AI for social good and AI in social science, but also like, decision support systems for medical technology, and methods of kind of using the feedback and integrating that feedback in technical ways. And I mentioned unit testing and sandboxing. We need methods of evaluating and testing AI systems sort of holistically or realistically before they're deployed. Finally, we need human-centered norms, standards, and governance. I know a lot of people as well, and we need other forms of oversight. And so we have this train, test, validation norm of how we evaluate AI systems, but we need a lot more norms like that that are easy for technical people to understand and implement in order to make systems more responsible. And I want to mention before I dive into a couple of my works, this source of bias in ML. And this bias, I'm not really, it's not the one to inquire about this, but there's this bias in ML that applied research is not novel. It's really complicated and difficult to do, but it's boring, and it's mostly someone else's problem. So we as AI developers, or maybe I see Rohan laughing, statisticians, don't want to deal with the messy real world. And it's not novel anyway, it's not real science. And pure research is this novel, groundbreaking thing where you don't really need to think about the real world or take it into account. And it's very exciting and motivating, and you need to be really smart to do pure research. And Alan Blackwell, I don't know where he got this chart from, but I think should be widely adopted in machine learning, that these are not, you should think of these as two axes, not as two opposed possibilities. So if you think of these as two different axes, you might put people like Edison, who were doing very applied research, pure research over here. People boring pure research. I think he was just, a monk or something. And then people like their responsible AI development belongs. It's not just, it is a form of pure research to be developing new methods that work for responsible AI development. All right, with that justification, I'm going to zip really quickly through a bunch of works, and you can either ask me to pause for questions if you're interested in something, or once I've gone through them, of methods and experiments for understanding learning behavior. This paper, a close look at memorization networks.
Hey, Tegan, it's Rohan. I'll just interrupt. I'm just going to kill your video in the
um,
hope that that might help with some of your
what
bandwidth situations.
Oh, sure, yeah. Should I? You're gonna kill my video. Stop video. Yeah, sorry about that. Do you hear my voice better now? Maybe. Do you hear me?
Yeah, we can hear you. Yeah.
Oh, okay, cool. Yeah, so the takeaway of whether deep networks memorize or generalize on training data, or what we showed in this work, is that the behavior of the neural network, whether it memorizes or learns patterns in the data, depends on the data distribution. So faced with data that is random noise, a neural network will memorize it and is able to get good training performance, although of course not good generalization performance. But faced with real data examples, neural networks will learn patterns that generalize to training data of other real images. Sorry, my slides aren't advancing here. There you go. Another paper that's presented at CVPR in 2017 is a data set and exploration of models for understanding video data through fill-in-the-blank question answering. So I call this fill-in-the-blank question answering, but now you might see it more commonly as masked language modeling. And now that system that I mentioned called BERT, which forms the basis of Google search results, that uses masked language modeling. And this is just, if you've ever done a Mad Libs as a kid, this is blanking out certain words in a phrase and getting the AI model to fill them in. So transforming the specification of the task from having to learn the whole video or the whole natural language statement to transforming that to one of filling in a blank. And the takeaway that we had in this work from 2017 was that this kind of simple predictive task improves representations. And we also had an extensive human evaluation, but I think better than any evaluation we did in a way is that in practice, this works really well enough for Google to use it in all of their search results. Another paper from a little while ago at iClear 2017 is zone out. If you've heard of dropout, this is a method for feed-forward networks that randomly sets some connections to 0. But that doesn't work for temporal data that you would model with an RNN, because if you set zeros in the transition matrix of the RNN, you'll have vanishing gradients over time. So people never used dropout with RNNs, and but if you needed regularization for an RNN, you had to use other methods that maybe didn't work as well as dropout did for feed-forward networks. And we developed this method called zone out. It's a very simple idea that instead of randomly setting things to 0, setting activations to 0, you set them to their previous value. And that works well. And the takeaway here is that randomness is good for robustness. And dropout has a lot of interpretation about this, about dropout training a pseudo, what's called a pseudo ensemble. So it's like an ensemble of different neural networks that you create by kind of subsampling the network by having these zeros in it, and zone out does the same thing. More recent research that is in under review right now that I'm happy to talk more about is, does under specification incentivize systems to cause distributional shift? So does it incentivize auto-induced distributional shift? So auto-induced distributional shift is distribution shift that is caused by the actions or presence of an algorithm. You can think about this in content recommendation of like a content recommendation algorithm could change the distribution of user interests by presenting content that is more or less interesting, or it could even drive away hard to predict users, changing the distribution of users. And this kind of behavior is obviously problematic in a content recommendation setting, which we study in this paper. And we don't have a solution or a broad solution, but we develop unit tests that can help diagnose whether or not an algorithm would use, is vulnerable to or likely to use to cause distributional shift in order to achieve performance. I haven't mentioned this much so far, but I'm really interested in helping solve problems of climate change. And this was one of the first works at a major tech conference to use ML for climate data. So the data in this case is sort of like a big video of the atmosphere over 80 years. It's the output of a climate model. And we're trying to use deep networks to recognize extreme weather events. And basically this worked quite well. And there's been an explosion of interest in this area that I'm really excited about. And partly that is due to this awesome organization that I'm very happy to be part of. I co-founded it, called Climate Change AI. We organize workshops and other community events. We recently launched a grants program for funding work at the intersection of climate change and AI, and basically getting machine learning people or people in AI who have expertise that could be helpful for solving climate problems to do that effectively. And we have this big review paper that was recently published by ACM that the way that this works from a user perspective is you identify the area that you're working in here in the columns, go down, and then whenever there's a dot, you can see an area that your skills might be useful in. My most recent work, published work, is like many people, having to do with COVID. So it's developing a private and distributed mechanism for using representation learning to give an early warning signal of disease, and then using that in a smartphone app to do what we call proactive contact tracing. And I don't want to go through a lot of details here. But yeah, the overall setup is that we have this detailed agent-based simulation that we made in partnership with some virologists, epidemiologists, doctors, etc. We use that to produce training data, where the training data has these individual level latent variables like symptoms and test results and characteristics like pre-existing medical conditions. And it also has individual latent variables like your current viral load and infectiousness. So then we can use that as labels for a deep model to predict, instead of needing to run this very heavy agent-based simulation. And then we get individual level predictions for infectiousness that in a pre-trained model that can be deployed on an edge device like a smartphone, so that they can cheaply predict individual level risk and use that risk to give a recommendation. For instance, if your risk is high, of like stay home, don't go to the grocery store, that kind of thing. And there are a few challenges we encountered. So like there will be distributional shift if your model works well in the distribution of diseases, because if your model works well at averting infections, then you'll see a different distribution of infections during deployment time than you saw during training. And we have a really dumb solution to this that actually works pretty well, which is just to iteratively retrain several times. So in simulation, we deploy the algorithm, generate a new round of training data, retrain the model with that, and then repeat this whole process several times. And I think there's a lot of potential to do something better there to deal with the distributional shift. And oh yeah, if you're curious if it works, yes, it works quite well, this method. The thing that works really well about it is that it's able to avert about as many cases as you would have if you had no trace, sorry. It averts more cases than other methods you could use for contact tracing, but with very little, what's called false quarantine. So we do very little prediction of like telling people to quarantine when they don't have, in fact, have a disease. And this is what produces a lot of like pandemic fatigue for people if they're being recommended to like not do stuff all the time when they might know very well that they are perfectly healthy. So as you can see here, the no tracing baseline is the dark, like blackish gray line. And these two are the deep learning based proactive methods, basically able to leverage weak signals to make very targeted predictions. All right. Those are all the works that I wanted to talk about. Oh, and this one, a recent report, there's a huge multi-institution paper on practical mechanisms for increasing for the trustworthiness of AI systems. The practical way we're doing that is making mechanisms for supporting verifiable claims. So when an institution or an AI developer makes an AI system, they might have some claims about how their AI system works, but if those can't be verified by normal people or an external third-party regulator, then it's not very useful to be able to make those claims. I don't want to go into the future directions in detail. I just want to give plenty of time for questions, so I'll end there.
Thanks, Tegan. That was great. I'll stop your sharing, and then maybe do you want to put your video back on? I mean, if you want.
Sure.
Our first question, and we'll record this one and then we'll turn the recording off, is just, do you have any books that you would recommend?
Yes.
I know that you
actually,
are a books person. So
I'm very much a books person. I love books. If you want to put my slides back on, I prepared a slide that has my main recommendations.
Oh, I'm sorry. I think you'll have to do it. Sorry, that was my fault. Sorry.
Oh, yeah, no problem. I forgot about it, actually. Are you seeing it now?
Yeah, we've got it. Thank you.
Okay, great. So a recent one that came out that talks about alignment, the term that I mentioned, really readable book called The Alignment Problem by Brian Christian. It's really well written, really like takes an anecdote-based approach. It has some really cool stories about the origins of AI. I really enjoyed reading that. Another one is Braiding Sweetgrass by Robin Wall Kimmerer. This is about the relationship or the sort of contrasts between indigenous forms of knowledge, indigenous wisdom, and scientific knowledge. So the author is both a scientist and a member of, I forget, an indigenous community in New York. And the book is just great. It has a lot of traditional knowledge and sort of useful insight about how to combine that with scientific more scientific, traditional scientific mindset for the benefit of both. Two books that I really recommend, I don't know, just everybody in the world to read are White Fragility and So You Want to Talk About Race, especially for us in an academic context. We're in a system that has been set up by colonial powers, and if we want to make that sort of equitable and good and just for everybody involved, I really think it's important for everybody to kind of take on reading these books and doing the best they can to help address those historical issues. And two others that I really enjoyed in the past few years are The Overstory by Richard Powers. This is fiction. It involves a lot of trees. I really like trees, but it's not just about trees. It's just a great book. It won the Pulitzer Prize, I think 2 years ago or something. And the last one is one that maybe everybody is familiar with, but I think it just is worth repeating because it's so good, is Weapons of Mass Destruction by Cathy O'Neill. It covers a lot of research went into this book. I think it's so many practical cases of ways that algorithms are affecting our daily lives and the details of how they're producing or aggravating inequity. And again, really well written and presented really well. And it's only gotten worse from there. So it's a great starting point if you haven't read it already.
It's kind of amazing how early she was on this stuff, right? Like it's now 5 years. It's hard to believe. Right?
Yeah, like almost 6. I think it came out in 2016. So she would have written it, before that. Yeah, I was rereading it because I was going to lend it to somebody, and yeah, it sounds like it could have been written 6 months ago.
Yeah, she was so ahead of the game. Right, I'll stop sharing, and then if folks have other questions, Amy, are you sharing this or am I?